Hello, my name is Seiji Shah, and I am presenting our work on constrained dynamic movement primitives for safe learning of motor skills. As robots become more present in industrial and everyday settings, humans must be able to deliver robots instructions without explicitly programming them. Dynamic movement primitives, or DMPs, are a fast and relatively simple way for robots to learn complex trajectories from expert demonstrations. However, it is very challenging for DMPs to also learn other user preferences, such as constraints on the workspace boundaries and obstacle avoidance. Our method, constrained DMPs, or CDMPs for short, enables robots to learn DMPs from expert demonstrations while also satisfying these operational constraints. A typical DMP consists of a canonical system that tracks the system's progress as it evolves along its trajectory, a nominal attraction term to drive the trajectory to its final goal, and a nonlinear forcing term with weights regressed to mimic the nonlinear behavior in a given expert demonstration. We introduce perturbations to the weights of the nonlinear forcing term so that the DMP can admit a zeroing barrier function, or ZBF. What this means is that the DMP, with its modified forcing term, obeys a Lyapunov-like inequality involving the ZBF that guarantees that the DMP's trajectory will stay within a predetermined safety set. We solve a non-convex optimization problem to find the weights to satisfy this ZBF inequality. We demonstrate the effectiveness of our method in 3 domains. In our first domain, our user is guiding the robot arm to learn a block stacking task. When a wall is placed in front of the robot, while the unchanged DMP collides with the wall, our CDMP generates a safe collision-free trajectory. In our second domain, a DMP is fit to expert demonstrations of chess moves. We find that our CDMP, even in this more cluttered case, generates trajectories that allow the robot to execute the movement without collision. In our third domain, an expert guides the robot to draw shapes. Here we see the CDMP is able to generate trajectories that are qualitatively similar to the ones given by the expert, while still avoiding the shaded regions. To recount, we present our method, constrained dynamic movement primitives, to generate complex trajectories learned from expert demonstrations while also satisfying constraints on the robot workspace. We verified our method in a wall jumping task, a chessboard task, and a drawing task on a Canova Gen 3 and Mitsubishi Assister robot. In the future, we would like to extend our work to non-Euclidean spaces, such as SR3, and more complex constraints, such as the robot joint limits. If you have any questions, you can reach us at the email down below. Thank you.